Hello there, welcome back. We're going to go through some of the questions that you'll be facing when you're being tested on aircraft fuel systems. Modern aircraft depend on clean fuel for safe operation. This Canadian regional jet is refueled using a truck-mounted pressure fueling system. Multiple filters and valves ensure that clean fuel is loaded into the proper tanks. Early designs used gravity feed to supply the engines with fuel. All those designs had their tanks located above the wing and in biplanes in the center of the upper wing. The picture shows an Etheridge Taube with a cylindrical fuel tank mounted above the fuselage. Pretty clear in the picture. Modern aircraft fuel systems are complex. We've got complex turbine engine systems with 3 types of pumps, several types of filters, a cross-feed system, pressure return lines, bottom pressure refueling with digital readouts, all going into or out of several different tanks at the same time. A Boeing 747 at average takeoff weight burns 4,000 gallons of fuel per hour. That reduces down to 67 gallons per minute, or even further, it would be over a gallon per second. The fuel system can handle 5 times that. It can handle 5.5 gallons per second. 2 types of aviation fuels are in general use today for civilian aircraft. Aviation gasoline, which in here it's going to be the first 3. It's known as avgas, and each one of the red portion of the labels do say avgas, aviation gasoline. And that's used in virtually all reciprocating engines. And with the LL, the low lead, that's going to be pretty much the primary one that is used. Kerosene type fuel, usually referred to as jet fuel, in this case Jet A, is used in turbine engines. And there's a few other colors, as you can see. Red, there's a purple, some are being phased out. There's a table that you can refer to. Avgas consists almost entirely of hydrocarbons. That's compounds that consist of hydrogen and carbon, hydrocarbons. Aviation gasoline is a highly refined hydrocarbon fuel obtained by fractional distillation of crude petroleum. There's a little bit of an indication on how fractional distillation works, from the thinnest or the gaseous down to the thickest, like the tarry asphalts. Important characteristics are purity, volatility, and anti-detonation qualities. We talk about each one of those a little bit in detail. Starting with purity, some impurities in the form of sulfur and dissolved water will also be present. A small amount of sulfur is going to always be present in crude petroleum because it's left after the process of turning crude oil into gasoline. And of course, it's normally treated already. But the water cannot be avoided because gasoline is nearly always exposed to moisture in the atmosphere. Each fuel farm, large or small, has a series of quality control procedures to reduce fuel contamination. And like small airports today, this fuel farm has only 2 types of fuel: avgas, low lead 100, and Jet A. Well, I see Jet A over here. And I can see avgas in the red, 100 LL. All right, I just didn't look that close earlier. So that's purity, the detonation qualities. You want basically the the fuel to do what, the optimum that it can do, and that is to actually ignite at the right time and power through the system, uh, reach a peak, and then to taper off. You're going to have less problem with your engines, your cylinders, pistons. However, if detonation occurs, the cylinder pressure is going to fluctuate dramatically. An engine experiencing detonation in the field should be investigated. It's usually a pinging or a knocking sound, and you are going to have a little more trouble hearing it out on the airfield because of the propeller tip noise. Detonation does cause an increase in cylinder head temperature because of the high pressure, and in order to help the fuel not detonate, you can add substances, predominantly lead. Detonation occurs in an aircraft engine when the fuel-air mixture inside the cylinders reaches its critical pressure and temperature and explodes rather than burning smoothly. The extreme pressures produced by detonation can cause severe structural damage to the engine. Various grades of aviation gasolines differ in the amount of additives they contain. The basic additive is TEL, tetraethyl lead, which increases the critical pressure and temperature of the fuel. And you can presume that 100 LL is low lead. So basically, TEL improves the anti-detonation characteristics of the fuel, and it also provides additional lubrication for the valves. How may the anti-knock characteristics of a fuel be improved? A, by adding a knock inhibitor. B, by adding a knock enhancer. Or C, by adding a fungicide agent. So it's the anti-knock characteristics. So that's not going to have anything to do with the contamination of a fungicide agent. So knock inhibitor or knock enhancer. Well, you don't want the knock to be louder, so it's a knock inhibitor, A. All right, so purity, detonation, and volatility. Volatility, it's basically the ability of a liquid to vaporize. Certainly, you need a vapor stream of fuel in order to actually ignite. Liquid gasoline will not burn. It must be vaporized, so it'll mix with the oxygen in the air and form a combustible mixture. So aviation gasoline must be volatile enough to sufficiently vaporize in the engine induction system. If it does not vaporize readily enough, it can cause hard starting, poor acceleration, uneven fuel distribution, and excessive dilution of the oil in the crankcase. If it vaporizes too readily, it can cause vapor lock, which will prevent the flow of fuel to the engine. The volatility of the fuel and thus its propensity to the condition known as vapor lock can be measured with a Reed vapor pressure tester, such as the one shown with a gauge and a sample on the bottom. The actual limits that are allowed, vapor pressure limit for aviation gasoline must be 5.5 to 7 psi's at 100 degrees Fahrenheit. That's lower than most automobile gasoline, which can produce vapor pressures twice that, 14 psi at the same temperature. If the vapor pressure of the fuel is too high, like with automobiles, it's likely to vaporize in the lines in hot weather or high altitude and starve the engine of fuel. Which you do not want to happen in the air. True or false? If aviation gasoline vaporizes too readily, fuel lines may become filled with vapor, and cause increased fuel flow. Not increase, but the vapor would be a vapor lock, and it would kind of prevent or decrease fuel flow. So false. In the other half of the true false, a measure of a gasoline's tendency to vapor lock is obtained from the Reed vapor pressure test, which is a true statement. What is the maximum vapor pressure allowable for aircraft fuel? Is it 7 psi, 5 psi, or 3 psi? The maximum now. You remember the range? The range was 5.5 to 7, so the maximum would be the 7. The vapor pressure of aviation gasoline, is it lower than the vapor pressure of automobile gasoline? Or is it higher than the vapor pressure of automobile gasoline? Or is it approximately 20 psi at 100 degrees Fahrenheit? No, it's more like 7 at 100. And it is less or lower than automobile gasoline. So vapor pressure is around 7, automobile is around 14. Aromatic fuels, these additives are no longer available, but basically performance aircraft would use fuels with special additives that actually would have a type of corrosive effect on the hoses or rubber gaskets, and so they would have to develop special hoses and gaskets for those type of aircraft that uses those type of fuels. There still may be a question floating around on these, but other than that, possible question, I don't think you have to concern yourself much with these. Here's that question in case it's still around. What is one disadvantage of using aromatic aviation fuels? Is it a fuel intercooler is required? B, it deteriorates rubber parts. That's the ticket right there. Or C, it results in low fuel volatility. So it deteriorates rubber parts. B, aromatic. Fuel weight, certainly if you're doing weight and balance calculations, you may be told what the weight of a gallon of fuel, and even that differs at temperature. But generally, Jet A weighs 6.7 pounds per gallon, and 100 low lead avgas weighs 6 pounds. So you can see Jet A is a little heavier, and it's not, it's still a gallon, so technically it's the same volume, but it is a thicker, more viscous type fuel. It does say the density of jet fuel varies more widely than the density of avgas with variations in temperature. However, this chart doesn't necessarily show that. It's showing aviation kerosene jet A dropping. But at the bottom, there's aviation gasoline 100-130, which does seem to vary about the same. All right, I might be missing something. But jet fuel density does become an important factor when fueling large jet transport aircraft. So technically, if you're already fully loaded, you may not be able to fully load the tanks as you would in warmer weather. I mean, you can quickly see the illustration here. It's 25 degrees centigrade. Taking that up, Jet A is going to end up weighing 6.75 pounds per gallon. So if I'm going to put 100 gallons in, I can use this conversion and figure out what type of pounds I'm putting in. How does temperature affect fuel weight? Is cold fuel, is that heavier per gallon? Or warm fuel, is that heavier per gallon? Or is there no difference in the temperature has no difference or effect? Well, we know temperature does. Pretty much think of the way the line went down. As the temperature increased, the weight went down. So, and you may instinctively think that warm water weighs less than extremely cold water or ice. But you can see there is a difference, a good 10% difference. Cold fuel is heavier per gallon. Turbine fuel has its own issues, and mostly that is because of its nature being a little more viscous than the avgas. It has a tendency to kind of trap water a little differently. At least with avgas, the water will settle in the bottom. But it doesn't necessarily happen with turbine fuel because it's a little thicker. It's more gelatinous, I guess. It has a different molecular structure and retains water in two principal ways. Some is dissolved into the fuel, similar to regular avgas. Other water is entrained in the fuel. Basically, the water kind of gets trapped in its own little layers. The greater presence of water in jet fuel allows microbes to assemble, grow, and live in the fuel. And actually, it's not much of a life, but these little things like living in jet fuel. Isn't that wonderful? Why are jet fuels more susceptible to water contamination than aviation gasoline? Jet fuel has a higher viscosity than gasoline. So far, so good. B, jet fuel is lighter than gasoline. No, it's the opposite. Or C, condensation is greater because of the higher volatility, which has no correlation one to the other. So yes, it's because the jet fuel has a higher viscosity, so it is more susceptible to water contamination. The water remains suspended in the fuel and does not settle out into the fuel tank sumps. Here's some more illustrations of what microbes can do. Large tanks of many turbine engine aircraft have numerous little areas where the water can settle and microbes can flourish. Areas between the fuel tank and any water that may come to rest in the bottom of the tanks is where the microbes thrive. They form a visible slime that is dark brown, gray, red, or black in color. And we got a little bit of a illustration off here on the side, the biomass and the sludge. You can see the different colors. This microbial growth can multiply rapidly and can cause interference with the proper functioning of filter elements and the fuel quantity indicators. Moreover, the slimy water microbe layer in contact with the fuel tank surface provides a median for electrolytic corrosion in the tank, in a metal tank. There are additives available. Prist is probably the most widely known. It's also the anti-icing, and it has the antifungal or fungicide ingredient to inhibit bacterial growth. So you kind of get two things done for once: anti-icing, which is covered in another class. The use of turbine fuels in aircraft has resulted in some problems not normally associated with aviation gasoline. One of these problems is A, increasing viscosity of fuel as fuel temperature lowers at altitude, B, higher vapor pressure, or C, microbial contaminants. Okay. Well, we've been talking about the microbial contamination, and that's mostly with turbine fuels, and those are the two together. I know sometimes it blends together, and one kind of looks like it might work also, but we didn't talk about any about the viscosity actually changing at temperature or altitude. So basically, microbial contaminants C. Final answer. Another question on microbial growth is produced by various forms of microorganisms that live and multiply in the water interfaces of jet fuels. Which of the following could result if microbial growth exists in a jet fuel tank and is not corrected? So what could happen? Could there A, or not really A's, are they? One, that'll interfere with the fuel flow. I suppose that's possible. B, interference with the fuel quantity indicators. Yes, that's actually the most likely. C, engine seizure. You're not going to have that problem. 4, electrolytic corrosive action in a metal tank. Yes, I like that also. So far I like 2 and 4 the best. 5, lower the grade rating of the fuel. Or C, electrolytic corrosive action in a rubber tank. Well, that's just a throwaway right there. So that means I guess we throw away C just because it's the only one that has 6 in it. So I did like 2 and 4. So far it looks like A. 1 was also good. B has 3 and 5. Well, 3, engine seizure, and lowering the grade rating. I'm not exactly sure what they mean by that. But I'm not going to try to guess that it fits the answer. So 1, 2, and 4, A sounds good to me. It looks like that's what it is. It will interfere with fuel flow and with fuel quantity indicators, but more importantly, can start electrolytic corrosion in metal fuel tanks. What can be done to eliminate or minimize the microbial growth problem in an aircraft jet fuel tank? You can add that anti-icing, Prist, some sort of well, let's see what they say. Use anti-icing and antibacterial additives. Yes, I like that the best. B, add CO2 as a purgative. Or C, keep the fuel tank topped off. Um, Now, that is a good way to try to avoid as much moisture in the air coming into the fuel tank, but that doesn't necessarily eliminate or minimize the microbial growth problem. You have to use something like PRIST, anti-icing A. Okay, there's a review. I'm going to post, I'm in negotiations to post these separately, so we'll see how that works. Some supplemental materials. Always set in time here. All right, we have some time, so let's go into other type of questions that you may or may not see. Some are, oh, they're good educationally. They might not necessarily appear on tests that you're going to see. The readiness of a substance to turn from liquid to vapor, is that known as its A, vapor lockability, B, detonation, C, combustion, or D, volatility? That word is volatility. Um, yeah, the ability of the fuel to vaporize. There's some illustrations right there. Depending on the nozzle, the fuel nozzle, you can kind of see where the vapor is. In this case, it's the bluish area, and the liquid is the black area. And the more red there is, the richer, and the more blue is leaner. You can see different patterns here. So volatility is quantified by the tendency of a substance to vaporize. Volatility is directly related to the substance's vapor pressure. At a given temperature, a substance with a higher vapor pressure vaporizes more readily than a substance with a lower vapor pressure. Four. A deposit or hot spot in the combustion chamber can lead to, and we didn't really cover this much in the book, the textbook does, but it is possible. You should know the deposit or the hot spot. Now, that's not necessarily detonation. It's kind of the other partner of detonation, and that's pre-ignition. There's a hot spot in the combustion chamber. It's kind of like the spark plug going off quicker. It's going to pre-ignite the air fuel mixture. As opposed to detonation, which has more to do with the vapor pressure of the fuel. Volatility, viscosity, just words that are related to fuel. But once you sort these four words apart, you might see a question on each one of them. So just basically be aware of each one. Volatility is the ability to vaporize, and viscosity is the ability of a liquid to flow. All right, I forgot I had this on pre-ignition. Combustion is a precisely timed and properly functioning ignition system. In contrast, pre-ignition is where the air fuel mixture ignites too soon. Covered. It's caused by hot spots in the cylinder. That might be because of a small carbon deposit, maybe a cracked ceramic spark plug insulator, or any other type of damage within the combustion chamber. When pre-ignition exists, An engine may continue to operate even though the ignition has been turned off. In extreme cases, pre-ignition can cause serious damage to the engine in a short period of time. And that's the biggest indication. The engine continues to fire after you turn it off. Of course, you can imagine after a period of time that can cause quite a bit of damage. The most readily available blend of avgas 100LL is dyed. What color was that? Was that purple, straw, red, or blue? Yeah, I guess you're going to have to know your colors. Purple we didn't really look at much. We did see it in the chart. Straw, that was the jet fuels. So it comes down to red or blue. LL is the blue. The red is, I think, 80. Yeah, so 100 LL is blue. 100 without the LL is green. But there may be a question on it, so let me not jump ahead. Grade 100 LL aviation gasoline is colored. We just answered that. That's blue. The existence of more than one fuel makes it imperative that fuel be positively identified and never introduced into a fuel system that is not designed for it. The use of dyes in fuels helps aviators monitor fuel types. 100 LL avgas is the avgas most readily available and is used in the United States, and it is dyed blue. Some 100 octane or 100/130 fuel may still be available, and it is dyed green. And you also see the red one on here, the 80. Which of these fuels have the highest water content and therefore is more conducive to microbe growth? The highest water content. Now, I like the second part. What fuel is more conducive to microbe growth? And I'm more inclined for the Jet A answer. So basically, because the other three are avgas, I'm going to go with the Jet A because it in general is more conducive to microbe growth, not necessarily because it has the highest water content. Purity issues related to turbine engine fuels are unique. While avgas experiences similar issues of solid particle contamination and icing concerns, the presence of water and fuel-consuming microbes is more prominent in jet fuel, which has a different molecular structure and retains water in two principal ways. And I believe we've already talked about that. I believe this was supposed to be a early use of a JPEG figure. A bug test is used to A, test the fuel viscosity, B, test whether two types of fuels have been mixed, C, test for bacteria and fungus in fuel. That's, I think, where you can use the slang bugs. Or D, test for fuel lead levels. So bugs, you're looking for bacteria or fungus. Bug test, I guess, is going to be commercially available. Basically, you're mixing it up matching the color. The basic differences between the grades of aviation gasoline is it the TEL, or is it the heat energy, or the specific gravity? Okay, the basic differences. Since you can probably just look at this as what's the big difference between avgas and jet fuel is my initial guess, as opposed to the octane ratings of the various avgases and the TEL content. But let's see what the best one would be. Or would it be the heat energy or the specific gravity? Well, I guess the big difference is going to be the heat energy. Yeah, I could get this one wrong. Ooh, it's just the TEL. All right, well, not sure where I found this question. Obviously, I don't remember much about it, but and I see now why I included it. Okay, the basic difference between the grades is the tetraethyl lead. All right, I'm not sure I love this question, mostly because I guessed wrong. Here's that chart again. Purple is something 115 being phased out, or it is already phased out. Even the 100, the green, is being phased out, and certainly is the 80, or the old rating of 8084. The blue, 91, gone. Now blue is the dye is being added to the 100 LL, and that is available. All right, so I guess this is good because it does show that each one of these avgases does have a different TEL, or tetraethyl lead content. I could see, low lead has 2, when the old grade of 80 had less than that. All right, that's interesting. I guess I didn't actually know that, so learning along with yous. A measure of the volatility of an aviation gasoline is its, okay, this is volatility. Keep in mind that that's the ability to vaporize. So what is that? It's octane rating? No. Boiling point? No. But vapor pressure. That's what you measure to determine the volatility of aviation gasoline. Read vapor pressure tester. Right on cue. The maximum vapor pressure allowed for aviation gasoline at 100 degrees Fahrenheit is B, 7 psi. The range is 5.5 to 7. Here's a close-up of the read vapor tester reading. So you don't want to go over 7. You may go all the way to the end here for automobile gasoline. If the vapor pressure is too high, it's likely to vaporize and cause vapor lock in the lines, which can starve your engine of fuel. The anti-detonation characteristics of aviation gasoline can be improved with the addition of TEL, A, tetraethyl lead. old ethyl brand, which was kind of the premium fuel that is still available at a lot of service stations. A civilian turbine engine fuel that compares with the military JP4 fuel is, so which one of these three civilian fuels kind of compares with the JP4? And I know we didn't really cover this. Maybe your extended readings you did. But I'd probably be guessing. Let's go ahead and take a look at it. It is Jet B. Yeah, when you guess, it could only go one of three ways, and chances are a couple years later you're not going to have the same guess. I do believe they're similar in that they can be operated at much lower temperatures. So the lower you go down in the JPs and the jets, the lower temperature you can reach. So if you run across a question like that, maybe that's one way to think about it. There's two basic types of turbine jet fuel: Jet A, Jet A1, and Jet B. Jet A and A1 are similar to commercial kerosene, and they have characteristics similar to the military JP5. Jet B is a wide cut fuel because it's a blend of gasoline and kerosene fractions and is similar to military JP4. I see what I'm doing. I'm kind of explaining the question ahead of time. I have switched that since, but I'm already deep into this. So we're just going to hurry up and hit the finish line. Jet B does have the low freezing point at around 60 degrees, negative 60 degrees Fahrenheit. So the analogy stands. Turbine fuel holds water more readily than aviation gasoline. That's because turbine fuel is more viscous. Microbial growth in jet aircraft fuel tanks causes corrosion inside the tanks. That is because they're extremely corrosive. They react with the water to form an acid that corrodes the aluminum alloy. So far, so good. Or they form a scum, which holds water in contact with the aluminum alloy in the tank. I suppose that's more precise. Yeah, okay. That's what happens. And there was no forming of an acid. All right, that was, I guess I added that just so that we can come close to the end of the time period. All right, very good. Thanks for hanging in there, and I'll see you on the next one.